Hey friends, this is Josh Price. I'm re-recording this 552 lecture from September 30th, 2020 in my office after class because we had some technical difficulties that prevented the Zoom broadcast from working and prevented the lecture from being recorded in movie format. So this will be good. I'll have another chance, have another go at it, and hopefully this will be useful to you. So today we're going to talk about thermodynamics. We've talked about the MO picture of bonding. We've got an understanding of how bonds can be described in organic molecules. Now we want to start making some comparisons between molecules. And there are some tools we can use that allow us to make these comparisons based on experimental data without necessarily resorting to high-level quantum mechanical calculations. When we talk about thermodynamics, we're talking about free energy. The change in free energy for a process describes whether it's spontaneous. Remember that delta G equals minus RT ln K. So the equilibrium constant for a process is determined by the free energy, and the free energy itself is equal to, for a change in free energy for a process, is equal to the change in enthalpy for that process minus your temperature times the change in entropy. And what does enthalpy mean? A change in enthalpy can be described as the change in heat observed due to changes in bonds and or non-covalent interactions. We've talked about bonds a little bit. We haven't talked about non-covalent interactions much. We're going to do that in a coming chapter. All right. So when a reaction happens, there's a change in enthalpy, which is related to the change in the energy of the bonds that you formed versus the bonds that you broke. To make these comparisons between molecules, we need a good starting reference point. And for that, we turn to these tabulated heats of formation. The heat of formation describes, for example, the reaction of making methane from elemental carbon and elemental hydrogen, and the delta H for that reaction is the heat of formation. And since and if we tabulate these for all molecules starting from their elemental precursors, we get values that we can compare versus each other. So, for example, we can compare in table 2.3 the heat of formation for ethane, which is minus 20.24, versus the heat of formation from propane, which is minus 24, and so on. And that in and of itself is not that interesting, but if you start making comparisons between these linear alkanes, you notice that for each new CH2 group that you introduce, the heat of formation changes in a predictable fashion. So, for example, going from ethane to propane, the heat of formation goes down by 4.6 kcals per mole. You see a slightly larger increment going from propane to butane, and so on. And if you do this for enough alkenes, you can come to the conclusion that adding a methylene group will change the heat of formation of your molecule by about 4.93 kilocalories per mole. Okay, well, aside from gee whiz, that's great. Who cares? And we'll, to be specific, I think the signs on all of these terms should have been negative. I don't know why they're not in that table. So who cares? And the answer is we don't often have the time or inclination to take every new molecule we make and calculate and do the experiment to determine its heat of formation. However, if we have enough tabulated values that can take into account the heats of formation of enough different functional groups, including methylene, but perhaps methyl and other interesting functional groups, then we can begin to estimate the heat of formation of a molecule and then compare that to the heat of formation of other molecules, and then we can have some measure of their relative stability, whether one's more stable than the other. So table 2.4 presents a number of group increments and these are group increments for heat of formation. And the way these are written is a little bit difficult to interpret. Your first letter here refers to the kind of atom we're talking about, and then in parentheses next to it are the things it's bonded to. So the first entry in our table would be referring to a methyl group that is bonded to one other carbon. Okay, we'd be talking about that methyl group. Similarly, for the next entry in the table, we'd be talking about a CH2 group that's bonded to two other carbons, where we're not saying what those carbons are bonded to. And a couple other points. D here, CD means a double bond, so this would refer to a carbon that's bonded to two other hydrogens in a double bond, and then because you've said CD, the fact that it's doubly bonded is implied. And you can see that this is summarized for lots of different functional groups. For example, oxygen bonded to two other carbons, as in an ether. And the group increment is only for the atom or functional group to which it's referred. So, for example, this number, minus 23.2, refers to this oxygen and not the carbons to which it is bonded. All right. And if you have questions about what some of these functional groups mean, you can go to the text and look at the table. A simple example of, and I wouldn't expect you to memorize these, but it's useful to know where they are and know how to use them. As a simple example, let's take this interesting molecule shown here, the benzene ring with the isobutyl group hanging off of it. We notice that there are 6 carbons in the benzene ring, and 5 of them are bonded to hydrogens. So let's see where we can find that entry in the table. Coming over here, there is a benzene carbon bonded to hydrogen, and the number value is 3.3 kcals per mole. So we go ahead and do that math here, and that tells us the contribution of the 5 carbons of the benzene ring. We have a 6th carbon in the benzene ring that is bonded to another carbon. So we come back here and we see a benzene ring that's bonded to another carbon, and we see its group increment of 5.51. We have in orange a carbon that's bonded to a benzene carbon, 1 other carbon, and 2 hydrogens. So if we come over to this list, we need to look for a C, followed by a CB in parentheses, another C, and then 2 H's. Okay, so that's the value we're looking for. We have in green a methine CH. That is a carbon bonded to hydrogen and 3 other carbons, a tertiary carbon. We look here, and the number minus 1.9 is the one we're looking for. And then finally, we have 2 methyl groups, and we've identified their contributions here, minus 10.2. So you put it all together, and you get a number that compares pretty well with the experimental number. Now, gee whiz, who wants to know the heat of formation of this molecule anyway? Well, maybe you don't right now, but if you were going to do a reaction and you wanted to determine, is this reaction going to be exothermic versus endothermic, you could do that by calculating the heats of formation of all of your starting materials and all of your products. Another useful thing that these group increments allow us to do is to start asking questions about strain in molecules. So the types of strain that we'll be talking about include angle strain, say in cyclopropane, where we have to have internal carbon-carbon angles of 60 degrees versus, say, cyclohexane. Where each of the internal bond angles can be close to tetrahedral because of the chair conformation. So there's angle strain. There's also torsional strain, which can come from gauche versus anti-type interactions that occur in conformations about carbon-carbon bonds. And there are other kinds of strain that we'll talk about later. But these group numbers are calculated in strain-free contexts. So were determined in strain-free contexts. So if you take a heat of formation based on these, calculated from these group increments, and then compare it to what's experimentally observed, the difference you can often attribute to strain or perhaps other electronic factors. A great example of strain is comparing the heats of formation calculated by group increments for cyclohexane versus cyclopentane versus cyclobutane, cyclopropane, versus what you see experimentally. If we go up to our table, the methylene group contributes 4.93. All right, so we would expect for cyclohexane 6 times minus 4.93. Instead, we observe minus 29.9. So the difference is marginal. We might say that cyclohexane has no strain. In contrast, go to 5, multiply 5 by minus 4.93, and you get the number 24.7 as the predicted strain-free heat of formation. The actual heat of formation is around minus 18, 6.4 kcals per mole higher. And we attribute that 6.4 kcals per mole to strain. Okay, so we would say that cyclopentane is more strained than cyclobutane. I'm sorry, we would say that cyclopentane is more strained than cyclohexane. If instead we go to cyclobutane, and again 4 times minus 4.93, and compare that to the observed heat of formation plus 6.7, we conclude cyclobutane has a strain energy of 26 kilocalories per mole. And you can think of that energy as being stored in the molecule relative to its linear counterpart. And we would say that cyclobutane is way more strained than is cyclopentane and than our cyclopentane and cyclohexane. And we see a similar but a slightly larger amount of strain by doing the analogous calculation in comparison with experimental data for cyclopropane. All right, we'll come back to this kind of analysis, but this is a good way of estimating. Using these group increments is a great way of estimating how strained a molecule is. All right. Now, sometimes we can predict whether a reaction is endothermic versus exothermic if we take the sum of the heats of formation of products minus the sum of the heats of formation of the starting materials. But in many reactions, only a few bonds are changing, and it seems like a shame to have to do all the math to figure out what the change in energy or enthalpy is just for those few bonds. And because of that, we turn to a slightly less unwieldy method, and that is comparing bond dissociation enthalpies. All right, what does that mean? What is a bond dissociation enthalpy? Bond dissociation enthalpy is the change in enthalpy, we'll call it BDE, for the reaction where a bond cleaves in a homolytic fashion with each atom taking an electron with it. And we'll talk about using this bond dissociation enthalpy for other purposes. But if you, as you've done in sophomore organic, if you write out a reaction and compare the strength of the bonds that you break versus the bonds that you form, then you can estimate what the free energy change or what the enthalpy change for the reaction should be. So suppose I take methyl iodide and I react it with water to get methanol and HI. I'd need the right bond dissociation enthalpy, wouldn't I? All right, so from our table, the bond dissociation enthalpy of methyl iodide is 57. The bond dissociation enthalpy for water is 119. The bond dissociation for and it's for the bonds that I'm showing you in red. And then in blue are the bonds that we made. In the case of methanol, I'm looking at our table and I don't see it. So I will turn to my OChem textbook and go look in the appendix to see what we can find. When in doubt, look it up, or perhaps rather Google it. Dun, dun, dun. Okay, the carbon oxygen bond in methanol is, sorry about that folks, 93 kcals per mole. And then the bond dissociation enthalpy for the bond in HI is 71. All right. So we can look overall and see whether this reaction's thermodynamically favorable. We're going to take the bond dissociation enthalpies of the bonds we're breaking, and those energies are positive, minus the bond dissociation enthalpies for the bonds that we're making, and we do that comparison and we can come to a conclusion as to the overall level of stability. So if we make that comparison, we come to the conclusion that this reaction would be endothermic by about 12 kilocalories per mole. All right. So we can use bond dissociation enthalpies in this way, and we can directly sort of compare how stable each of these bonds is. And you can think of bond dissociation enthalpy as being sort of how far down, when you mix two orbitals together, how far down in energy do they go, roughly. Now, some people are interested in using bond dissociation enthalpies as measures of radical stability. For example, it is more uphill to go to methyl radical than it is to go to ethyl radical. Why is that? You might be tempted to conclude that it's because the ethyl radical is more stable than the methyl radical. However, you have to also think about differences in the stability of your non-radical starting materials. And because the heat of formation of that non-radical starting material is known, and the same is true for the hydrogen radical, if you know the BDE and you know these two, then you can calculate heat of formation of the radical. And correcting for differences in heats of formation of the starting material in these bond dissociation reactions allows you to get more directly at radical stability. And if you compare enough molecules, you can also derive group increments for radical stability. Group increments for heat of formation for radicals. So examples, of using this information, let's go ahead and compare the stability of T-butyl radical versus the regioisomer primary radical. Okay, and if we were to calculate what we've got here, we have 3 methyl groups, and we have 1 tri-substituted radical. So, and the way this table is going to do that is like this. So I guess I'll use the same sort of systematic nomenclature that was used earlier for our heats of formation. So we're going to use those heats of formation from the previous table as well as from the radicals to give us this information. Here we have 2 methyl groups. We have 1 CH group, and we have 1 primary radical where the radical is connected to 1 carbon and 2 other hydrogens. So with this information, and let me look up the numbers for the methyl group again, minus 10.2. And the multiply that by 3. Wait. The single CH group is minus 1.9. The primary radical is plus 35.8, and the tertiary radical is 38. So do the math, and I'll get out my calculator so that we can. 2 times minus, let's see, 2 times 10.2 equals plus 38. Okay, so this is uphill by 17.6 kilocalories per mole, the heat of formation of the tertiary radical. We do the same math. Oops. Except Joshua doesn't know how to do math. We uphill by 7.4. We do the same thing here. And we conclude that the primary radical has a heat of formation of plus 13.5 kcals per mole. Now remember, heat of formation numbers are relative to their elemental precursors, but we could make that comparison between the two, and we could say that in terms of heat of formation, the tertiary radical is 6.1 kcals per mole more stable than the primary radical. All right. So remember that number. We're going to come back to it. More substituted radicals are more stable because of sigma to p hyperconjugation. In our valence bond theory model, if we go with our QMOT model, this is mixing of the pi CH3 orbitals with the p orbital of your radical. Depending on whether it's planar. If not, it would be like the sigma out. All right. One interesting aside is that if you want, there's a difference between thermodynamic stability and kinetics. That is, there's a difference between how stable a radical is versus how long it remains unreacted in solution. So here's some actual numbers for the half-lives of various radicals at room temperature at a 10 micromolar concentration. And perhaps not surprising to compare methyl radical, which we know is less stable than T-butyl radical. Nevertheless, there are some radicals that can last much longer than T-butyl radical. For example, replacing those T-butyl groups, tri-tert-butyl radical, sorry, that's not the T-butyl radical, that's the tri-tert-butyl radical. That would look like this. And if you compare the half-life of that, which is 8.4 minutes, versus the half-life of the secondary precursor, it's 1 minute. And the question is, can that totally be explained by the difference in radical stability we just looked at above? And the answer is probably not. And there is some extra kinetic stabilization going on here due to sterics, bulky groups getting in the way of reactions. And there's an example in your book that you should look at. I mentioned it briefly in class, but honestly, you can get more out of the book's discussion than you could out of what I might say. So see page 85 of Anslin and Doherty, let's say 84 and 85, for an illustration of this principle that radicals with nearby sterically bulky groups tend to be persistent and last longer. For example, these two radicals are commercially available. They can be stored indefinitely, and they can be handled without any special precautions, not only because of the resonance delocalization, but also because of the nearby sterically bulky groups. All right, with that, I want to talk about carbocation stability. For carbocations, instead of bond dissociation enthalpy, we're going to need a different measure because carbocations are different from radicals. So the measure for carbocation stability will be the change in enthalpy for this heterolytic bond cleavage between a carbon and a hydrogen to leave the carbocation or carbenium ion and a hydride. And we're going to call this number hydride ion affinity, HIA. These numbers are going to be positive because the way we've written this reaction with the hydride leaving the carbocation behind, that's uphill in energy. In some ways, calling it a hydride ion affinity is a little bit deceptive. Really, it's hydride ion leaving group ability in the context of carbocations. But in any case, hydride ion affinity describes, to some extent, describes the stability of the carbocation. Larger hydride ion affinity numbers mean less stable carbocations. So there's a few interesting points of note here. You see the usual trend that a primary carbocation like ethyl is less stable or is more destabilized than a secondary carbocation, which is more destabilized than a tertiary carbocation. And at first blush, it looks like those differences are huge. 273 versus 246, a change of 33 kcals per mole. And then going from secondary to tertiary, another change of around 15 kcals per mole. But it turns out with carbocations, you have to be careful. These numbers are in the gas phase, which basically means you've got the carbocation in the vacuum, no other molecules near it. And it will turn out that for similar carbocations, the larger the molecule is, the more stable the carbocation is. For example, look at this series of primary carbocations: ethyl, propyl, butyl. And look at the numbers and the changes. For ethyl, you start out at 273. Then if you add another methyl group on the other side, or if you add a methylene group in between the carbocation and the methyl group, you go down by about 7 kilocalories per mole. And then if you go from ethyl and from propyl to butyl, there's not as much of a change. So it appears that adding nearby carbons tends to stabilize even a primary carbocation. And this effect is what's known as self-solvation. The carbocation is desperate to be surrounded by something with a dielectric constant better than a vacuum, and so even the presence of nearby electron density in the form of other functional groups can somewhat stabilize a carbocation. And because of that, the most rigorous comparisons we will make will be between carbocations that have similar structures, similar numbers of carbon, but it'll have key differences. For example, let's compare this primary carbocation with 3 carbons. It is a primary carbocation versus, I don't know what color we want to use, versus this tertiary carbocation with a similar number of carbons. So we go from here to here. That is a change of 34 kilocalories per mole. All right. Well, what about primary versus secondary? Can we make that comparison? So let's look at the N-butyl carbocation versus the similar butyl carbocation where the positive charge is on the more substituted carbon. And you see that by going from 265 to 247, we're downhill by about 18 kilocalories per mole. So in general, it's thought that if you go from primary to secondary, that's downhill by around 17, and going from secondary to tertiary, that's downhill by about 17. I'll point out that these are gas phase numbers, and they are exacerbated by being in the vacuum. In solvent, these effects are attenuated, and these energy differences are smaller. A couple other trends of interest include resonance stabilization. As you would expect, resonance stabilization is what am I trying to say here? As you would expect, resonance stabilization is stabilizing. That's intelligent. Here we have on the top of this table the allyl carbocation with a HIA of 256. Compare that to the similarly sized but non-resonance stabilized propyl cation, resonance stabilization worth about 10 kilocalories per mole there. One interesting observation, if you compare the stability of this allyl carbocation versus the secondary propyl carbocation, Turns out that the secondary propyl carbocation is actually more stable than the allyl carbocation, at least in the gas phase. And for this simple molecule, it appears that being on a secondary atom is more stabilizing than being delocalized. However, as you start to go down this series of allyl carbocations and start to add functional groups, add substituents on these carbons that each bear part of the positive charge, as you increase the substitution of the carbocation, these numbers, hydride affinity values, go down, meaning you're increasing instability and you're already substantially more stable than a typical secondary carbocation. These aren't numbers to memorize, but you should be able to rationalize these trends based on arguments that we've talked about before for carbocation stability. Other notable features, primary carbocations are, vinyl carbocations are frequently very poor in stability. And this might reflect the fact that, or rather, the vinyl carbocation is way less stable than the ethyl primary carbocation. And this might reflect the fact that, I'm going to cross out this hydrogen and draw a carbon-hydrogen bond. We would expect this carbon to be roughly sp hybridized. You've got a more electronegative carbon there where you've got a positive charge, and that's destabilizing, so hydride affinity will be higher. Other interesting effects that we'll come back to will be the ability of nearby heteroatoms to stabilize or destabilize a positive charge, the donating group ability of the nitrogen is superior to that of oxygen, which is superior to that of fluorine because of their increased electronegativity. Putting a pi electron withdrawing group like the cyano group adjacent to a carbocation destabilizes it. Aromaticity can stabilize carbocations, whereas the cyclopentadienyl cation would be anti-aromatic and has a much higher hydride affinity value. One interesting comparison to make is here between these two norbornyl carbocations. So here you have a secondary carbocation and a tertiary carbocation with similar numbers of carbons. Now, we would have expected to see a lower hydride affinity by about 17 kcals per mole for the tertiary carbocation. Nevertheless, the difference is only downhill by 6. And that might suggest that there's something special about this secondary carbocation. It might be unusually stable. So to explore that possibility, we need to return to a discussion we were having in Chapter 1 about so-called 3-centered but 2 electron bonds. So here's the secondary carbocation, and I'm going to number atoms 1, 2, and 3. Okay? Those are the 3 centers, and then these here, the electrons in the sigma bond between 1 and 2, are the 2 electrons involved in this 3-centered 2-electron bond. And what we basically have is working with a hybrid valence bond MO theory approach, you've got a carbon-carbon sigma bonding orbital, and it's on the same side of the molecule and can align with the adjacent empty p orbital on the carbocation. And when you have a filled orbital overlapping with an empty orbital, we would normally say that that's just hyperconjugation. But in fact, there's evidence that the electrons in this bond between 1 and 2 are actually delocalized, almost as though you've got a pi bond between 2 and 3 and a sigma bond between 1 and 3. So we're going to draw a dotted line here and a dotted line there. And in fact, maybe, oops, I erased too much stuff. Maybe we'll take that original bond and put a dotted line there, and we'll put a positive charge in the middle. You've got 3 atoms, 2 electrons, and a positive charge. This would be called a bridged carbonium ion in the lingo we used in chapter 1. We might also call it a non-classical carbocation because you have bridging of this atom between 2 different carbons, or perhaps more accurately, well, let's look at the resonance structures. So if I take the starting structure for norbornene, and I move these electrons over, I would get the following resonance structure. With my positive charge here. And you should be able to draw the other resonance structure there. So using hydride affinity values, we're able to tell that the norbornenyl carbocation is more stable than expected for a secondary carbocation, and that provides evidence for this non-classical carbocation argument that we've been talking about. Okay, with that, we need to stop. I will see you tomorrow for your exam. Until then.